Let's look at this problem. So we have a rigid pole. The pole itself has neglected weight and diameter, and we see two forces acting on the pole. Those are the applied load. And we need to determine several things. First, the angle between the two forces FA and FB. B, we need to solve for the fixed support reactions at this point right here. And C, we need to determine the magnitude of the moment produced by force FA about an axis OD. So in order to do any of these, we need to represent the two forces as Cartesian vectors, and we're going to do our Cartesian calculations. So one thing at a time. For FA is directed from point A with coordinates of 0, 0, and 4. So 0, 0, and 4 meter for point A. And then it is directed to point C, and that has coordinates -1, and then 4, and 0. And FB is directed from point B, that'll be your 0, 0, 4 plus 1.5, so 5.5, to point D, and that will be coordinates 2, -3, 0. Therefore, the position vector from A to C equals to endpoint minus initial point, that's -1i, and then plus 4j, and then minus 4k in the unit of meter. Therefore, your unit vector UAC equals to RAC vector divided by its magnitude. So we're going to take -1i plus 4j plus k divided by square root of 1 square plus 4 square plus 4 squared. The units cancel out, the meter and meter cancel out. So this will give you negative 0.174 I plus 0.696 J minus 0.696 K unit vector. Same thing for B to D, end minus beginning. So that's going to give us 2I minus 3J minus 5.5K meter. And we can do the same thing to find UBD, to take the position vector divided by its magnitude, and we get 0.304I minus 0.456J minus 0.836K. So now, to find the angle between them, all you need to do is to find the dot product between UAC and UBD, and then find the inverse cosine. So inverse cosine equals to the dot product, UAC and UBD. So to calculate that, you'll take these multiplied together, so negative 0.174 times 0.304 plus 0.696 times negative 0.456, and then plus the two negative and negative cancel out, so it's simply 0.696 times 0.836. And whatever inside the parentheses, that's going to be a scalar. It should be less than 1. If it's more than 1, something is not right. And then take the inverse cosine of that. The answer is 77.8 degree. So that's your part A. If you say, well, But the part A says that it's the angle between the two forces, FA and FB. You found the angle between two unit vectors. Doesn't matter, it's the angle between these two directions. All right, UAC and UABD represent the directions of FA and FB. For part B, we need a free body diagram because we're trying to solve for support reactions. So we have two forces that have already been, well, actually not yet, but we are going to do that, that need to be represented in vector, Cartesian vector form. But at point O, we have a fixed support. Fixed support provides maximum restraints. Therefore, it exerts two vector unknowns, a force, I'm just going to call it FO, and a moment unknown, MO. Okay, so I'm going to draw a little hoop here to represent that this is a couple moment. So FA and FB can be determined. Okay, so your FA equals to your magnitude of 250 Newton multiplied by your UAC. So I'm actually not going to write all that, but that's your unit vector UAC. So as a result, you multiply the 250 Newton to each term of your UAC, and that's going to give you a negative 43.5I plus 174J minus 174K Newton. Same thing, FB equals to the magnitude of 175 Newton times unit vector UBD, and that will give you 53.2I minus 79.8J minus 146K Newton. Okay, and then your resultant force as a vector equals to your FA plus FB plus your unknown FO, and that equals to 0. So from there, you can solve for your FO as a vector, just doing, I guess, vector subtraction. And then you will get a negative 9.7I minus 94.2J plus 330K Newton. That's part of the answer. That's your support force reaction as a Cartesian vector. Okay, so how do you calculate that? FA plus FB, both of them are known, plus this one right here has to equal to 0 because the pole is in equilibrium. Now moving on to determine the resultant moment, we can write our equation to be resultant moment about point O equals to 0, and that equals to the moment caused by force FA about point O plus the moment caused by force FB about point O plus the unknown support MO, that is the support reaction provided by the fixed support at point O, and that has to be 0. So this is our unknown that needs to be solved, but MA can be determined by your position. We're going to use the vector formulation, position vector from point O to A. So this will be our position vector, and that is 4K position vector cross your FA, which is this right here. Okay, so with the calculation, this equals to negative 696I minus 175 J in the unit of Newton meter. So this is because moment is calculated as position vector R cross force vector. Same thing, we can calculate the resultant the moment caused by the force Fb about 0, which is a different position vector. Remember, your position vector has to start from your reference point and it has to end on the line of action of your force. So we're going to use this position vector right here. And that is your 5.5 K cross FB. FB is determined earlier already, and carry out the vector calculation. This equals to 439 I plus 293 J Newton meter. Don't forget this one plus our unknown MO has to be 0. From there, you can solve for support reaction MO. That equals to 257 I minus 119 J in the unit of Newton meter. So that's the second answer for this part. So we solved for our support reactions, 2 vector unknowns, and if we have to use a scalar formulation, the 2 vector unknowns break down into 6 scalar unknowns, right? But in this problem, it makes more sense to work with the vectors directly. Part C, determine the magnitude of the moment produced by force Fa about the axis OD. So for part C, just remember you have this moment right here, which is ma about the axis OD. This equal to some kind of moment. Okay, this position vector can be anywhere from the axis OD to anywhere along the force Fa. So in this case, we might as well use what we did earlier. We choose this 4K right here. Might as well use the result that we did earlier. Okay, choose this right here. So this will be the moment caused by Fa about 0. Okay, and then from there, we're going to attach the unit vector of OD has to be the unit vector of this direction, and it's going to be a dot product. Okay, so from here, we're going to use the solution we had already. So that's our negative 696 I minus 175 J Newton meter that have already been calculated. Dot product of UOD. UOD is determined by position OD, so ROD divided by the magnitude, and ROD is a 2I minus 3J divided by the magnitude 2 squared plus 3 squared. And as a result, this is going to be a scalar result of negative 240 dot to give you 3 significant figure in the unit of Newton meter. So that's the answer right here. Why negative sign? Negative sign means that the moment created by the force Fa about the axis from O to D, that is going to be a clockwise rotation. Visually, you can tell that it is indeed a clockwise rotation. So for this step right here, if you say, can I set up my matrix and use the matrix method? You can. But because we have already calculated R cross Fa from the previous step, we might as well use that. Okay.